Hi everybody, welcome to week 6 of the course. Last week we looked at chapters 4 and 5, some of the building blocks you need for the HR model. This week we're continuing with looking at chapter 6, which is also another building block needed for the HR model. So overview what we're trying to do. In essence, most of this chapter is about building the blocks needed to show the Repzinsky's theorem. Right? That's a core component of what the HR model is. So we're going to try to relate factor abundance and production volume to each other. And in order to do that, we need an Edgewood box, which we will be showing over the next few slides what that is about. And we will be needing or using the contract curve in the Edgewood box to derive some optimal point. So what does the Repzinsky theorem says? It says that any increase in the quantity of a factor of production at constant final good prices, meaning final goods prices not changing, will lead to an increase in the production of the good using that factor intensively and decrease the production of a other good. So if we look at it in terms of example, say the amount of labor rises. So remember, what do we need to remember? We need to remember that food is labor intensive and manufacturers are capital intensive. So in our case now, when labor is rising, the output of food would increase. So we're going to be producing more food. But what are we going to produce less of? Where's the output going to fall from? In terms of the manufacturers. On the other hand, what happens if the available amount of capital rises? Then the capital intensive good manufactures, the output of that would increase. And the production of the labor intensive good would fall, which is food would fall. So what are we going to show in the next few slides graphically is the Edgewood box. And we're going to build some of the foundations we need. We're going to take it piece by piece and then put everything together. So that's what happened over the next few slides. You can look at the alternative name of what they call this. It's not so important. Edgewood Pauli box. So that was the other contributor. But because of the length of the name, people just call it by the first author in a sense. So we're going to link, what the Edgewood box does well, is link all the available inputs, capital and labor, into one figure. And all the production. So we're going to link food, and we're going to link manufacturers with their capital and labor respectively into one figure. Yes, you can use other types of information, other combinations than that, and also use the Edgewood box. We're just using this for specifically for the type of products we have and the type of inputs we have. So we can assume, and it doesn't really matter, we can assume that we are relatively capital intensive. We're going to assume alpha is 0.7, and that's the alpha relating to manufacturers, and the alpha relating to foods is 0.3. We don't necessarily need it to add up to 1 for what we are doing. In our case, we're just going to keep it added to 1 when we add the alphas. It's not important for the Edgewood box. So we're going to start our Edgewood box by showing the family of isoquants that would represent the manufacturing sector. So initially, when we started our work in the previous chapters, we had an isoquant of m equal to 1. So that's the standard one that we see appearing here. And then anything where we're going to increase the isoquant value from m equals to 1 to m equals 2, we're going to have a rightward shift of the isoquant. Similarly, the same thing will occur for when m is equal to 3, we're going to have a rightward shift. Remember, this is the capital intensive good. So the shape of this isoquant will look slightly different from the food sector. And we'll find that predominantly when we compare the two, we'll find that the manufacturing sector one lies a bit more towards the capital side, while the food isoquants will lie a bit more to the labor side. But the shifts in isoquants when the values increase, when the amount of production increases, is always towards the right. So we're going to depict the food isoquants family. We're also going to start with the food quantity is held equal to 1. And we're going to show that similarly when food equals to 2 and food when F equals to 3 that they are rightward shifts. Nothing too crazy. All we're having is how the isoquants look, where we have capital on the y-axis and labor on the x-axis. Together, so we combine the isoquants of both the food industry and the manufacturing industry. As you remember, the blue lines depict the manufacturing industry, which is more capital intensive, and the red lines depict the food industry, which is more labor intensive. So this is just the combined version. What you should recognize is both of these industries have different goods that they produce. So their outputs differ. But what do they have common? Their inputs are common. Labor and capital is used in both industries. But it's important thing that for you to recognize is that there is a fixed amount of labor and capital that is available in a country. So that labor and capital needs to be shared between the food industry and the manufacturing industry. And that is where the Edgewood box comes into play. So what is going to happen that instead of having the blue set of isoquants and the red set of isoquants in the same orientation, we're going to flip the food industry's orientation on the graph. And that's what's going to happen on the next few slides. So all that we do now is change the orientation of the food industry. You can change the orientation of the manufacturing industry too, but we just need to change one of them. So in our example and in the textbook, we change the orientation of the food industry, and we're going to flip this at or rotate this at 180 degrees. So basically, we're going to have an upside down version of the labor industry. Why are we able to do this? We're able to do this for the idea that the amount of labor in the industry is fixed. Whatever is used in the manufacturing industry leaves a certain amount left. And whatever that certain amount that is left is then used in the food industry. So both inputs, whatever is used in the manufacturing industry, the remaining amount from the total amount of inputs is then used in the food. So now, with the flipped version of the food industry, the origin for the food industry changes. The point where it uses zero capital and zero labor changes. For the manufacturing industry, it's still in the bottom left corner on our system of axes. So that is represented by OM. But for the food industry, the origin is now OF, which is the top right corner. So this is the point of zero labor and zero capital for the food industry. We're going to now assume there's a point A. At point A, for the manufacturing industry, they use Km amount of capital and Lm amount of labor. So what does that mean? If in the manufacturing industry they're using Lm amount of labor, the amount of labor then used in the food industry at point A is the total amount of labor called L minus the labor used from the manufacturing sector, which is L minus Lm. And this will represent as LF. Similarly speaking, in terms of capital at point A, the amount of capital that they use in the manufacturing sector is Km. Therefore, automatically, the amount of capital used in the food industry would be the total amount of capital available in the market, which is represented by K, minus Km, which is the amount of capital used in the manufacturing industry. And we will call this Kf. So remember, the total labor used in the food industry and that labor used in the manufacturing industry will add up to the total labor available in this country. And that same thing would apply in terms of capital. So based on the Edgewood box, let me use a similar point A in the previous graph. Point A, we found out that there is a certain amount of capital and labor that is used in the manufacturing industry with a remaining amount of labor and capital used in the food industry. How do we then determine what production levels we produce? And these are determined via the isoquants that passes through point A. If you look at isoquants relative to the OEM origin, the manufacturing origin, the blue isoquants, will determine how many product is produced for the manufacturers. Similarly speaking, if we look relative to the food industry origin, the red isoquants will determine how many food or output is produced in the food industry. What is the problem that lies with point A? And that we're going to cover. So we have the issue. Point A, unfortunately, is not an efficient allocation of inputs. The amount of capital and labor used at point A can be better used to actually produce more in both or in either sector. So what can we do? So let's assume we want to hold the food quantity constant. We want to stay on the red isoquant and we move to a point B. At point B, what we find that then we are actually on a higher isoquant in terms of the manufacturing sector. So we were able to change the amount of labor and the amount of capital that was available in the manufacturing sector. How did we do that? From A to point B, what did we actually do? We reduced the amount of labor and shifted that to the food industry. At the same time, what the food industry did was, in exchange, released a certain amount of capital towards the manufacturing industry so that we can produce at point B. What has happened in the food industry? Besides the changes in capital and in labor, nothing actually has occurred. We are still producing on the red isoquant. But in the manufacturing sector, what has now occurred? That shift of resources has allowed the manufacturing industry to produce now at point B, which lies on a higher isoquant. So we've actually increased the output in the manufacturing sector just by relocating the inputs between the two sectors. So point B here represents the contract curve. So these are all the efficient input combinations, and which we're going to find if you were taking different hypothetical examples, that would be this green line that we eventually would draw. And we'll find the curvature of this green line would be dependent on how capital intensive the manufacturing sector was. So remember, B is an efficient point, which lies on the contract curve, which is the efficient input combinations. And these will only occur at the points where the red and the blue isoquants are tangent. Anywhere else, if we were not on a tangent point, we would be able to relocate inputs between the two industries to be able to produce a bit more in at least one of them or in one of the sectors, if not both sectors. So, as I mentioned earlier, the contract curve would differ depending on how capital intensive the manufacturing sector is. Remember, on the one side, if the manufacturing sector is capital intensive, the food industry would be labor intensive. So we see here is a diagonal OM and OF. That diagonal that is drawn from OM to OF represents the idea when the capital to labor ratio is equal to 1, meaning we use equal amounts of capital and labor. So that would be a contract curve in that sense. But if the capital intensity increases, the further away we will lie from the diagonal. So the closer towards that K letter we would move. So we'll move more towards the top left-hand corner. So that is just showing capital intensity increase and how a contract curve is affected by the capital intensity. So finally, we can move to the Repzinsky theorem. What you need to remember is the idea from chapter 4 and 5, which led from the idea of final goods prices. When you are given the final goods prices, you can determine the wage rental ratios, your slopes needed in your cost minimization process. So once you apply the cost minimization process from your wage and rental ratios, you can actually then determine the capital intensities in both the manufacturing sector or the manufacturers and in foods. So this is something you need to remember from the previous work in last week's work. Very important. What you also need to understand is what does the Repzinsky theorem says. It says that when the capital stock increases, what does it do? Capital stock increases will favor the industry which is capital intensive. Meaning here that when the capital stock increases, and in our case for the manufacturing sector, which is the capital intensive sector, then the production in the manufacturing sector would increase, but at what cost? At the cost of the food industry, where we'll find that the production would decrease. So that's very, very important for you to understand. So we're going to look at that theory. We're going to first start off from the idea, okay, there was no capital change. Where's our point of equilibrium? And then we're going to move the idea that capital changes from K0 to K1. The textbook has example where capital changes from L0 to L1 where the stock increases. You can easily be asked in the exam, draw a graph or analysis where we look at a capital stock decrease or labor stock decrease. So bear in mind this is something you take into consideration, go and practice it, because at some stage you can be given that to actually reproduce theory, but not exactly from the textbook. Okay, so the first 3 points here on the slide just deals with the idea that capital stock does not change your final goods prices as that is given, and therefore it would not affect your wage rental ratio, and therefore would not affect your capital intensities. So when a stock changes capital stock or the labor stock increases, it doesn't affect your maximization process in terms of determining your capital intensities. What is full employment? You need to understand, which is point 4 here. You need to understand that full employment is when all the capital in the manufacturing sector and all the capital in the food industry adds up to the total amount of capital. Similarly, this is for the labor industry, where the total amount of labor in the manufacturing sector and the food sector adds up to the total labor that exists in this country. And the fifth point here, which is the formula, which is just expansion of a formula, it says, okay, capital and labor ratio. How can we break this up? So what is capital equal to? Capital is equal to the capital in the manufacturing sector and the food industry sector. So that is the equal to sign. Capital of labor equals Km over L plus Kf over L. That was just breaking the idea of what capital is. Then what they do is to the first part, to Km over L, what they times that by is, this is now when we're looking at the next equal to sign, where we have the Lm over L times Km over Lm. What are they doing? So they're taking the Km over L and they're timesing that by Lm over Lm. So they're not actually changing anything. So they're introducing the labor in the manufacturing sector by not making any changes to the formula. Similarly speaking, what are they doing to the Kf over L part in the equation? They are timesing that by Lf over Lf and then just rearranging. So what is happening in that fifth point is that they are just rearranging the formula, breaking it up, taking all the ideas of what total capital is and what total labor is, and then timesing it by certain values to derive some type of formula that they want to do comparisons with or analysis with. In the end, they land up with that full equation there at the end, which is the lambda m km over lm plus 1 minus lambda m times kf over lf. So they're breaking the capital intensity in the manufacturing sector and the capital intensity in the food sector by using some lambda component. And what is the lambda component? It is just the proportion of labor in the manufacturing sector divided by the total labor that exists in this country. So we're just looking at trying to break up all the changes in the capital and labor ratio. Nothing too crazy. Look through the formula. It's just maths manipulation. They are just using some ideas. And if you really struggle with this breakdown of the formula, pop me an email and then we can Skype or we can Google Meets or WhatsApp call, preferably not WhatsApp call for my number, so Google Meets. We can do that and I can go through this formula and breakdown for you. What is important from this section is to understand the graph work that we're going to do. And you need to remember the chapter 5 and chapter 4 tools that we use in this Repzinsky's theorem depiction. That's most important. So we're going to look at initial equilibrium first. So we're going to assume there's no capital change yet. So we have K0 to represent the total amount of capital for this country, and we have L to represent the total amount of labor for this country initially, right? Before any changes occur. So we're going to draw our Edgewood box, nothing special. Remember in this case, the prices for outputs are given. The price that you're selling these products for or in the market is already given. So final good prices is given. So what does that determine? A capital to labor ratio for manufacturers and a capital to labor ratio for our food industry. So that's nothing special in that terms, but that's going to allow us to find our expansion parts. So the blue line here depicts the expansion path for the manufacturing industry based on its capital to labor ratio that was determined how? Via the prices that were given and then via the wages to capital rental ratio. Right? So it would not produce at any other place except on this blue line. Otherwise, it would not confine or conform to the capital labor ratio that will bring this market to equilibrium. This is for the manufacturing industry. At the same time, that prices that were given also determines the expansion part in the food industry. And that is represented by the red line, right? And we can see the capital labor ratio that exists for them. So what we need to know is that any other point that lies off these expansion paths will not produce it. These are not equilibrium positions in terms of the prices given, the wage rate to rental capital ratio is given, and it does not comply with the capital intensities that is represented by both the manufacturing industry and the food industry. Anyway, off these lines would be non-equilibrium. So we need to find the point where they intersect, because that is where the capital to labor ratio in the manufacturing industry is still on the blue line, and the capital to labor ratio of the food industry is still on the red line, right? So it's still confining to equilibrium, and that point then, which is point A, would then be equilibrium position, right? So that is the efficient allocation of all our inputs. That is the most important point. So we will produce a certain amount in terms of manufacturers there and a certain amount in terms of food there. So now we're going to move away from equilibrium, which was point A. What changes? What changes now is the capital stock increases from K0 to K1. Remember that even though the capital stock is changing, that does not affect the prices. Remember, prices is given to us. So we see that the capital stock has increased from K0 to K1. All that does is shift the origin for the food industry from OF0 to OF1. So shifting upwards. What doesn't change? Nothing else changes, right? The prices are remaining the same, which means that the capital intensities remain the same. So that means the slope or the gradient of the food industry will still remain the same even when the capital stock is shifting or increasing. So that would relate then to, in essence, to the food industry's expansion path shifting upwards, or following in the same parallel gradient as it was represented initially when there was no capital stock change. To sum that up, the gradient remains the same in the food industry when the capital stock increases. So that's why the red line is the same gradient or is parallel to the initial line that existed before. Okay, so what does that mean as our point of equilibrium now? Our point of equilibrium now is this new point, point B. That is where the two capital intensities for both industries is still on its expansion path, and that would be where the allocation of inputs would be efficient. But having said that, what does that mean in terms of output? What has happened in terms of output? So now we need to say, okay, what has happened in terms of our output? What has changed between the markets at our new point B, which is at full employment, which is the most efficient point that we can be based on the expansion path of the manufacturing industry and the food industry. So we can just measure the length of that blue line. So initially the line was OMA, right? That line now is extended from OMA now to OMB. So by the B point shifting further along that expansion path, that means what? That means we're actually producing more at point B in the manufacturing industry. Remember, if a line is moving further away from the point of origin, means that we're going to be on a higher isoquant. Right. So that's important. So the expansion or the movement along the line further is representing an increase in product for the manufacturing sector. But what is happening in the food industry? In the food industry, you're not actually now seeing a movement along that line further or lower. So we need to actually compare the length of the line that happened in the food industry versus the line in the food industry now when capital has changed. And we find that the length of the line OFO to the point of A is actually longer than the new expansion line OF1B. That meaning that the production initially before the capital increase was more in the manufacturing industry than it was now under the new capital shift on the capital stock increases. So that's the easiest way to see it. You just look at the length of the lines. And because that length of the line is now shorter, we're actually producing less food, which is exactly what the theorem says. So the theorem here shows that with the capital increase, we find that production has increased in the manufacturing sector, but unfortunately in the food industry, which is not as capital intensive as the manufacturing sector, the production has actually decreased. And that's your Repzinsky theorem. As I say, be prepared for alternatives where the capital stock decreases. Be prepared for where the labor stock decreases. There's no ways I'm going to give you the example from the textbook where the labor stock increases. So expect that if you were to get some form of regurgitation of theory, that it will require you to do something different from the textbook. Some actual work in a sense, not reproducing something that you just copy and paste. So some concluding remarks. The Edgewood box is good at summarizing input allocation decisions, and it's also a good way to show the contract curve, which is all the efficient input allocations. That means when all the capital is used entirely and all the labor is used entirely to produce the best possible output that can occur between the manufacturing and the food sector. We've also seen that an increase in the capital stock when final good price is given leads to manufacturers' production increasing because it is the capital intensive sector, and a reduction in the labor intensive sector of food in terms of its production. Similarly, if we were to look in terms of labor, if labor stock were to increase, then the food production would increase and the manufacturing production would decrease. So this is a Repzinsky theorem, and simple question that it could be posed in exam is, using the Repzinsky theorem and an Edgewood box, reproduce graphically with a bit of explanation how labor stock decreasing would affect the production levels in both the food and the manufacturing sector. If the food and manufacturing sector were the type of goods we're producing. Right? It can be any other type of goods, so just watch out for the phrasing. That's it for the week.